the area of a surface of revolution, or surface area. That's what we're looking at now. So, how we're going to start off with this is if we just consider something a cylinder. If you think of like maybe a can of soup or anything like that, just a can. If you think of how if the label covered the entire outside of it, if you were to undo the label, that's almost like a picture of undoing the circumference itself. So if we consider a can of some sort, okay, and if we were to cut the metal and unfold it, it would about look like the label that covers it. We could talk about the surface area or the outer surface of that guy. And so if we needed to calculate the surface area, oh, I see my ponytail in the shadow and it makes me, oh, it's fine. To calculate the surface area of this guy, we would just calculate the surface of the unfolded metal. And so this is a rectangle. So it's length times width, basically. But if you look at what created this length, it is this circle, right? This outer circle is, when you unfold it, that's what made this length. So this is really the circumference, 2 pi r. And this width right here is the height of the can or whatever it was. Okay, so that's what we have there to calculate the area in general. So area is basically circumference times height, if we consider it like a can or something, or we could call that circumference times width if we wanted to. We could call it that, or we could call it circumference times length. We could call it any one of those things. It's just a one-dimensional length. So I'll just call it length. Because now we want us to consider the surface area of something else. Suppose that we just had an XY axis here. And so let's just suppose that we had some curve here that went like that. Okay. If we took this curve and we rotated it about the x-axis, right here, we would get this mirror image. And it could spin, if we spun it, it would create a solid of revolution, and we could calculate the surface area of this solid. If that's what we're interested in doing. So if you look at this guy, let me make this showing. Okay, we could calculate this by considering all these different circle pieces. So if I take just a section out, let's take a section out of our solid of revolution. And so that's what this is about, the surface area of these solids of revolution. If we cut a little circle out of this guy, okay? And so if we looked at that piece, if you consider the area of this circle right here, it's going to have a radius. The radius is going to be from here to here, right? And so the circumference, which is what we're interested in here, of this is 2 pi r, where this is the radius. But if this is the x-axis that we've rotated against about, and this is the y-axis, the radius is from here to here. The radius is y in this instance. So the radius for this will be 2 pi y. Now if we take this section and then we take another one and another one and another one and we add up all of them, we're going to add up all of these, 2 pi y times the length. And the length is going to be the arc length that we talked about in the earlier section. So arc length is defined to be the square root of 1 plus dy dx squared dx. So this is the formula for surface area. If we're going from some part A to some part B, we can change this summation symbol into this integral symbol, A to B. This is the definition of surface area calculation. So I've written it just a bit differently on your sheet. I wrote it as, instead of y, I wrote f of x, and instead of dy dx squared, I wrote f prime of x squared. So these are just different notations. Now, when will these variables change? Okay. If you're rotating something about x, the radius is going to be y, okay? Now, if you have a function that is written, it's easier to write it as x as a function of y, then these are the things that will change. So if we've got, instead of f of x, we've got g of y. What will change with this little formula? Okay, we've got g of y. We will integrate from c to d, where c and d are somewhere on the y. Those are our limits of integration. It'll still be 2 pi y, but instead of, the reason I wrote f of x instead of y in that one, and I'm going to change it here too, is because we want it to be written in terms of x. So y equals f of x, we're going to write that. But if we want it in terms of y, we're just going to leave it as a y. And then this will be the same. It's going to be times the square root of 1 plus g prime of y squared, or dx dy squared dy. Okay, so what changes when we write our function as a function of y, and it's spun about the x-axis, is this radius is always a y distance. Either we write it as f of x or we write it as just y. And what will change are the limits and the differential. So we have a few examples where a function is written as x, and then one as it's written as y. And then maybe I spun one about the y-axis. We'll see when we get there. But that's basically what you have to change if you are writing your function as a function of y. So let's try an example. Example 1, the curve y is the square root of 4 minus x squared between -1 and 1 is an arc of the circle. X squared plus y squared is 4. Find the area of the surface obtained by rotating this arc about the x-axis. So there we go. Let's do that one. Goes like this. If we got, they gave us a little picture there, which is kind of nice. So we've got this picture. There's this little arc right here, and it's being rotated about the x-axis, like this. So we want to know the surface area of this guy. So we are going to integrate this guy from -1 to 1. And the surface area is going to be 2 pi. And it's been rotated about the x, right? So it's 2 pi y. But this is easily written. It's already written for us. Y is equal to the square root of 4 minus x squared. So it's already written in terms of x. So 2 pi y, I'm going to call this the square root of 4 minus x squared, okay, times the arc length, the square root of 1 plus dy dx, or y prime is, let's take its derivative, 1/2 4 minus x squared, 4 minus x squared, so the -1/2, chain rule times derivative of the inside minus 2x. This is y prime, but what we put in here is y prime squared. So I'm going to clean this up a little bit. Let's see. -2 divided by 2 is negative. So I have a negative x over the square root of 4 minus x squared. This is what y prime is. But if I want to square him, and I do, because that's what I have to put in here, this becomes positive. This becomes an x squared. The square root of something squared is just a something, 4 minus x squared. That's what we have there. So I'm going to put that right there. X squared over 4 minus x squared is what goes there. I've already squared that. And this is times, let me make some more room here, dx. All right, so it goes like this. I'm going to pull the 2 pi out here. I don't have to worry about that. Integrate from -1 to 1. This, watch this. This is the square root of something times the square root of something. We are allowed to distribute that in there. So let's do that. If we have the square root of a times the square root of b, this is the square root of a times b. And so if we, this shadow is really bugging me. I wonder if there's some way I can have it not be so shadowy. I don't know if that's, just whatever. Here, the square root times the square root is the square root of a times b. So this is the square root of 4 minus x squared times 1, or 4 minus x squared, plus 4 minus x squared times x squared over 4 minus x squared. These will cancel, and so I'm left with an x squared dx. So this cleans up so very nicely. X squared minus x squared is 0. We're just left with the square root of 4, which is a 2. So we really have 2 pi 2 dx. If we integrate 2 dx, it's 2x, and we'll evaluate this from negative 1 to 1. We get 2 pi times 2 times 1 is 2, minus 2 times negative 1 is negative 2. We get 2 pi times 2 plus 2, which is 4. So we have a 4 times a 2 times a pi. We get 8 pi. That is the area of the surface of this figure revolved about the x-axis. Okay, I'm going to pause and we're going to do the next few examples. Okay, example 2 says, find the exact area of the surface obtained by rotating the curve y is x cubed between 0 and 2 about the x-axis. So I'm going to draw just a little sketch so I can see sort of what it's supposed to be. The function y is x cubed looks like this, basically. It's kind of like that. All right, so, but we want it between 0 and 2. So this little area right here, from here to here, we're going to rotate this about the x, right? So if we rotate it about the x, it will be symmetric right there. And so what we're looking at is if you spin this around, you would have a surface that was formed. All right, it's going to be circular, circular, circular. It's going to have all these little circles. We could slice that up and see all the circles. So what we're interested in this time is not volume, but the surface area. So the surface area, S, is equal to 2 pi. If you look at the radius of this guy, it's a y, 2 pi y, times ds is something that stands, it's a short abbreviation for the arc length. So that's how we could talk about the arc length. So now I'm going to put in the details. So y is our radius, but it's written as x cubed. So I'm going to write this as x cubed. Okay. And my arc length is going to be the square root of 1 plus dy dx squared dx. So let's go ahead and figure out what is the derivative of this. So y prime, which is also known as dy dx, is equal to 3x squared. Okay, so if I square that, that's equal to 9x to the 4th. All right, so that's what I'm going to put in here. I'm going to replace this with 9x to the 4th because I've already done that work ahead of time. So 9x to the 4th. Alrighty, so this is what I've got going on here. Now, I forgot my this is an important part. This is the integral symbol that I need, and where am I integrating from? From 0 to 2. 0 to 2, so that's what I need to put there on. Alright, so we're going to integrate this guy. The 2 pi is simply constant. We can put it on the outside. So 2 pi, 0 to 2. X cubed 1 plus 9x to the 4th dx. Now this is a nice one because this is a very simple substitution one. So if we use substitution, that shadow is really a problem. I don't know what to do about that. My lighting stinks, I think. I don't know what to do. I move it higher. I just don't know. So hopefully we'll make it through this one. Let's see. Substitution is what I'll use here. And so u is going to be 1 plus 9x to the 4th. And then when I take du, I will get 36 x to the third dx. So now I want to rewrite this integral in terms of u. The 2 pi stays out there. I want x cubed dx, but I have this. I want to say divide both sides of this by 36. Alright, so now to get x cubed dx, I can get that by writing down 1 over 36, which I'm going to put that on the outside, du. That took care of that part. Alright, now I need to write the square root of 1 plus 9x to the fourth. Or this u, the square root of u, or u to the 1/2. And that took care of all of that. The only thing left to do is adjust my limits in terms of u if I choose to do that. And I do want to do that. So I'll say, if I let 0 go in here for x, 0 to the fourth is 0 times 9 is 0 plus a 1. This turns into a 1. If I put in 2, that's going to be 16 times 9. Oh my goodness. 16 times 9. Or, oh, it's 144. Plus a 1 is 145. Okay, that's what we get there. Now we just integrate. Integrate u to the 1/2. It becomes u to the 1/2 plus 1, 3/2 divided by 3/2, which is multiplied by 2/3. Evaluated from 1 to 145, and this is all multiplied by 2 pi over 36. And so then this will be 4 pi over 3 times 36. That's my constants. Let's see. Oh, that's a 3 times 36. Okay. 4 can go into this 9 times. So this is really a pi over 27 times, that's with the 2/3 multiplied by there, the square root of 45 cubed, of 145 cubed, minus the square root of 1 cubed, which is just a 1. And that right there is the surface area of this figure. All right, cool. This shadow's driving me crazy. I have to fix this. Okay, example 3. So it says, find the exact area of the surface obtained by rotating the curve. X is 1/3 times y squared plus 2 raised to the 3/2 between 1 and 2 about the x-axis. So we're still rotating about the x-axis, but our function is written as a y. So how will that change the setup? The surface area is still going to be 2 pi, the integral, 2 pi y. Instead of writing y as a function of x, instead of writing f of x here, we're just going to leave the y because we want everything in terms of y. And we change our limits of integration from x limits to y limits. So we're going to go from 1 to 2. Our surface area is going to be 1 plus dx dy. This changes instead of dy dx with respect to y. This is what the changes are. So we leave that as the variable y. Here, let's take this with respect to y, dx dy. So dx dy will be 1/3 times 3/2 times y squared plus 2 to the 3/2 minus 1, which gives us 1/2 power, times the derivative of the inside, which is 2y. So before, I need to square this, but before I square it, I'm going to clean it up a little bit. These 3's will cancel, so I have a 1 right there. These 2's will cancel, so I have a 1 right there. So I'm left with basically y times the square root of y squared plus 2. This is what dx dy is. But now if I square this, this will give me y squared times the square root of something squared times y squared plus 2, which gives me y to the 4th plus 2y squared. That is what this guy squared ended up being. So that's what I'm going to put under here. Alrighty, so under here it goes. I have y to the 4th plus 2y squared dy. Alright, So we have to integrate this guy. Let's see here. The 2 pi can come on the outside, and that's not going to be any trouble. Well, let's move that out. And here's this y. And underneath here, let's look at what we've got. We've got y to the 4th plus 2y squared plus 1 dy. So, what can I do with this? This turns out to be, I can factor it into perfect square trinomial. So if I factor this, this will factor nicely into y squared plus 1, quantity squared. Let's see, that's y to the 4th plus 2y squared plus 1. So this is the square root of this squared times y, from 1 to 2, 2 pi dy, and the square root of something squared is just the something. So this square root and this power 2 get canceled, and this is what I'm left with. So that's pretty great. I can distribute this y if I want to. That's going to be y to the 3rd plus y dy. I can integrate those very easily. This is 2 pi times y to the 4th over 4 minus y squared over 2, evaluated from 1 to 2. And when we put in our limits of integration, we get 2 pi times 2 to the 4th is 16, divided by 4 is a 4, minus 2 squared is 4, divided by 2 is a 2, minus, evaluated at 1, 1/4 minus 1/2. All right, we get 2 pi times 2 minus 1/4 plus 1/2 is plus 1/4. All right, we have 2 pi, this is really 8 over 4, plus 1, that's really 9 over 4. This is going to be 9 pi over 2. That's what I get the surface area for that to be. Let me check my notes just to make sure I didn't make a mistake. And, I got 21 pi over 2. Let me see what I did wrong here. Did I miss a chain rule? Hang on. Oh, well, that would have been fine. Let me find my mistake.